Okay, then I welcome everybody to this session, which is basically a working session and the continuation of the telltale STPA analysis, which we are doing on a weekly basis, more or less weekly basis within the automotive work group. So therefore, I'm very happy that Paul is supporting me here. So done a brilliant job so far on guiding us through STPA analysis and bringing the telltale use case forward. For those who have been in the previous session, the next 10 minutes will be just the general thing about the automotive work group, what the telltale use case is, why we've selected it. So you can take a rest for the next 10 minutes and recover from the last session. And if you're new, you should be still fresh, had an hour, 2 hours break. So therefore, just stay and listen a little bit. Yeah. So the introduction will be quite high level. First of all, I would like to start with our mission statement, just to say what we do in the automotive work group. And this work group discusses the conditions and prerequisites the automotive sector needs to integrate Linux and safety critical system. I guess it's a very high level statement. And what we do is we look into actual use cases. So from the capacity which we have, we currently focus on one use case, which is the telltale use case, and explain it very briefly on the next slide. And we check which technical requirements are there to the kernel and to the development process. And our investigation should be the input for the work in the architecture work group, the open source engineering processes, Linux features, and so on. But this was also brilliantly illustrated in the welcome slides, which Shu and Kay were presenting on the first day. And yeah, the outcome of everything should be a blueprint for actual projects in the future. And for this, we try to document all the work we have. So there is the work group repository, and also as we have work cooperation with AGL, the Meta ELISA layer to build the demo. Why is there the AGL part? Our telltale basically means the warning indicators like ABS brake, also the gear indicator, gear shifts, and so on. And this is some very common use case, a lot of devices, and where clusters were discrete in the past, the instrument cluster becomes digital these days. And for this, more and more systems migrate, come together. And while Linux was quite uncommon in infotainment like 10 years back, nowadays there are more and more Linux-based devices. It's also where AGL, Automotive Grade Linux, comes into picture, where they have infotainment and cluster demo use cases. And the nice thing about the telltale use case is that it's also typically combined with a lower ASIL level, which gives us a smoother start to discussion and not starting with a harder thing. And also that we have relaxed timing requirements on this. So we don't need to discuss about full real time on very microsecond, millisecond operation. Here we have reaction times larger than 100 milliseconds because it's basically display a warning sign in your instrument cluster and then being able to react on it. And if you consider when the light bulb goes on your car, typically the next thing is not that you switch off your car and go to the right, but you say, well, I take care of this later. So there's a little bit of time on this. And the nice thing about this is also there's potential interest by OEMs, tier ones on this, follows a trend. And there is a really large market behind it because every car gets nowadays a display for the instrument cluster. And if you can come away from certain commercial additional royalties, bring this into a fully open source solution, there's also benefit there in a cost-driven market. As we didn't want to reinvent everything again, we started with the AGL reference demo. Our hardware is mainly QEMU. We're still considering to go to a Renesas device, but for easy reproduction and for the analysis, we are still in the QEMU base, knowing that there is no external watchdog on it. Why this is important, we learned during the STPA analysis. Right. So then shortly, as I mentioned, STPA analysis, why are we doing this? We figure out that from OEM side, tier one side, there's not fully transparent information available. So we do a lot of analysis anyway, and we want to have a full understanding on use cases. And with the STPA analysis, which stands for System Theoretic Process Analysis, we do our system analysis and look into potential hazards and risk. For very simplified words, it can be a little bit compared to a hazard analysis risk assessment. Well, this graphical representation is a really nice one. And how this really looks like, we see later on the session part of Paul. If you want to learn more about the methodology itself, there is the handbook around. So it's really available, a script from the MIT. And also from this, I've just stolen the definition of it, which says that the STPA is quite a new analysis technology or technique, and based on the extended model for accident causation. And it also, the nice thing what I like about it is that it assumes that accident can also be caused by unsafe interaction of system components, even if none of them failed. And the authors also point out to some advantages. So it's a good start to also analyze very complex systems. The nice thing also here is that we can start in early concept analysis phase, also looking into pre-existing elements where we already have ideas on. It can help to drive also then detailed design decisions forward, include also software and human operators in the analysis. And for us, it's also a good server for documentation, because we were discussing a lot of things and then new people joined the automotive work group and ask, yeah, where's this, where's that, what is the item, how have you defined things? So we also get in a much better documentation, we just grab out and go on. And yeah, also it can be easily integrated into system engineering process, existing ones also. Not directly relating to the STPA, but overall, if you would like to join the automotive work group, always subscribe. We've currently 150 members not as companies, but individual persons who subscribe to it. You can also join our weekly calls. Currently, they are Friday, 12 o'clock UTC. So that's where we also discuss about the STPA analysis, but there's a tendency that it moves to Wednesday. All the documentation which you currently see can be found in the working group automotive repo on GitHub, along with the cluster demo. I guess also Paul will later on have some information. And yeah, the main source code repo for us is then the Meta ELISA. And as we do some work for the requirements analysis from the part, there's also safety concept tool, which was created by Jochen, who was the former automotive work group lead. And yeah, that's mainly it. The next one is just some marketing slide to show the current members of our automotive work group, which is Automotive Focus. And I'll stop sharing and give the time for Paul to present.
Thank you. And I will jump into the STPA. If I can remember how to share. Okay. So as Philip was saying, we're actually kind of recording the results of the STPA and all the documentation associated with it in the WG Automotive repository. This is the kind of the common work in progress thread, which I'll jump us to. And so this is part of the use case 2. So this is a kind of a second go at a safety concept after the initial implementation. And a useful place to start is kind of looking at the overall system context. So for those of you not seen STPA before, this is a control structure hierarchy. The idea is that you identify controllers and controlled processes as part of your system, and you identify the control actions that they interact with, but also the feedback. So that's the dashed lines going upwards, the feedback that's provided from a control process to the controlling process. This is the top level look at it. So we've got a system including an instrument cluster that's using a display. We've got a source of non-safety information that's going to be updated on the dashboard, but also sources of these telltales. So these are signals that indications that have a safety component to them, and clearly the display is providing information to the driver of the vehicle. So that's the user is kind of represented in this diagram as well. And we also have an external watchdog, which we'll see why that's necessary in a moment. So from that, we evolved this diagram. So this is focusing on the system, the software system on the SoC. We've got this external watchdog here. So the grey boxes are components that are outside of our immediate system that we're interacting with. And the blue boxes are interesting because these kind of represent really something that doesn't really quite fit with the control structure diagram, but is sort of important for our understanding of this system here, which is data models that are actually about exchange of information and interaction between cooperating control system hierarchies. And broadly speaking, you have telltale requests as well as kind of non-safety critical information coming from various components on the vehicle via CAN bus. These are all coming into this cluster application, and the idea of a request handler here to manage the telltale requests. And then there's really two parallel paths that we look at. One is the actual rendering of the telltales and the other display information on the display via the display controller. We've mentioned Qt here because the example application that we had for the first version was developed using Qt. The actual rendering of the display is done via a frame buffer and a display controller. But in order for us to have confidence in that, we've also got a readback mechanism where we have a set of telltales that we're checking for, and we're actually checking that they are being displayed the way that we expect them to in our current version of the display. Now, in earlier versions of this architecture, we had the readback interface actually being driven by the display. We've simplified it, not because we necessarily think that's the best safety approach, but because we actually wanted to consider something that we could implement as a demo and understand the limitations of it. But the principle here is that we're receiving a telltale request, we're recording which telltales we believe need to be displayed, and we're checking that those are actually being displayed at the moment. And if they're not, that's when we actually want to activate a safety mechanism, and we've gone for a very simple one here, which is to simply turn off the backlight. Thereby the driver realizes that something must be wrong because they can no longer see the things they're expected to see on the instrument cluster. And this is happening via the external watchdog. And the reason for that is quite simple, is that we don't believe that we can always rely on the operating system to be able to do that. There's a possibility that something could happen to prevent this telltale checking mechanism. So we have a requirement that the telltale checker is both regularly petting the watchdog to say, yes, I'm here and I'm functioning, but also that actually the watchdog is providing a challenge response mechanism whereby it's challenging the telltale checking algorithm to complete an iteration and give an appropriate response to confirm that it's not only that it's still there and waving hello occasionally, but actually able to perform its function. And if it doesn't satisfy those requirements, then the safety mechanism, the safe state of turning the backlight off is triggered. I think one of the things we talked about in the previous session that we identified as an advantage with this approach is that the real fundamental safety argument here is about the effectiveness of the watchdog. So that if we're looking at what we need the operating system to do, or the system to do, the software system software to do, it's in order to actually meet our safety goals, it ultimately boils down to driving this telltale checking, driving the watchdog from the telltale checker. Clearly, all the other functions are important in order to maintain the display and provide the information the driver needs. But as a fundamental safety net, it's the watchdog that's providing that ultimate guarantee, and that reduces the amount of possible interference that we need to consider between the various components of the system and our safety critical components. So this is the kind of the second step actually in the STPA process. So it's probably worth me stepping back and framing where we start, which is actually about identifying the purpose of the analysis. And we've already looked at this diagram here, which shows the system boundary. What is the system that we're considering? What is within our remit? And we identified from that we're actually looking at this instrument cluster system here, and the software system in particular. And then ultimately we're really interested in the safety angle here, and for STPA these are represented as losses. What is it? What are the losses that we want to avoid? And actually STPA can be used for more than just safety. These losses could be something about loss of mission for your system, as well as something with a safety element to it, or a security angle as well. But we're focusing specifically on the safety losses, which really boil down to this first one: loss of life or injury to people. And the next thing we do is we look at the hazards, which is sets of system conditions that might lead to these losses, and we document the ones that we're actually considering for our system, which is fundamentally about the driver not being informed about a system condition that might lead to a harmful event. But there are also some other losses, other hazards that can lead to losses as well. If our system causes some distraction in the display, that might also impact lead to a loss, lead to a collision. But also if our system doesn't operate effectively, if the warning's coming up all the time and the driver learns that warning isn't really valid, it's a false warning, then the driver might actually become desensitized to it because it's repeated so often, and might lead them to ignore it, and then that could lead to the loss. And there's also a possibility that the content on the display itself could compromise the driver, a flickering image triggering an epileptic fit. Now we've mainly focused on the first one in our analysis so far, but it's this is an illustration of when we're thinking about safety, you have to think about a broader set of goals or of hazards that you're trying, or risks that you're trying to manage. The next step in this part of STPA is to identify the system constraints. So that's the conditions that we need to be true in order to avoid these hazards. We boiled these down to these three constraints, and then the goal of the analysis that we then do on the control structure that I was showing you before is to consider in what circumstances these constraints might be violated, and then that leads us to say, what is it about the system that we need to have confidence in order to avoid that. Now we've only really got as far as drawing the control structure so far, so we're now starting to move on to some of the next stage, which is this idea of unsafe control actions, and I've got a couple of examples here. But I think the purpose of this session is to kind of get some more people engaged with this process, get some input from you, and work out how best to move forward with this. So I'll step back from this a moment and ask if there are any questions, or if anyone's got anything else they'd like to add. Okay.
So I guess one point which we could see in the figure was that there is the path to turn off the backlight, but there's no checking element in there also from our simplification, which we've made with the readback interface, because it's something where typically question could come up. We say, okay, we rely that the display controller will send the right data via the image buffers to the display. So I guess from real implementation, there's also something where we get the information from the display back if something was properly rendered and properly displayed, but we set for getting a closer fit to the demo and the system which we would like to look into. We keep it for this for now, because it's something important to be mentioned.
Yeah, I think that's it. I think that maybe that's something to talk about, is that with this architecture here, we're relying on this readback interface here, which is part of the whole of the system. So that there's sort of potential for interference between other parts of the system and this readback interface and return buffer here is still there. I think having that more independent. So in other words, if at this point we're relying that the frame buffer, the image in the frame buffer that we're reading to provide this readback interface, we're relying on the display controller and the operation of this mechanism over here to actually render that on the display. We'd have more confidence if we could actually get that information, get that confirmation from the display itself. But that was kind of presupposing the existence of a hardware mechanism to do that, which is a reasonable assumption, but not something we can implement.
There are two important points. One is that these diagrams in one way are quite deceptive, because one kind of relates the size of the boxes somehow to the complexity and contribution. And when you step back, the major contribution for telltale problems on the display is actually the rendering, because the rendering involves a graphics engine, and then depending what software you use to implement the rendering, it's going to be some more or less complex DirectX application or whatever. So the probability that there is a systematic fault inside the rendering software, which on a more fancier dashboard with Chrome effects or other effects, is just intrinsically complex, right? Also using libraries which most likely will just be at a QM level. So if you draw a fault tree, just a qualitative fault tree, I would put the highest contribution into the telltale getting mangled into the rendering. And then I would put the second highest into the application creating the object model, and then into the interaction of for example, bogus signals arriving, asking or forgetting to ask for telltales to be appeared. In my opinion, the display controller is really, it's hardware that is configured by software, but it is in very, very resilient. In particular, because even if there's a corruption inside the memories of the display controller, there is nothing inside the display controller as far as the data memory is concerned that is sticky. So the display controller actually fetches the data to put on the screen via DMA from the DRAM memory where the frame buffer resides. So I think this is one aspect that maybe we need a fault tree in addition to show what we're really focusing on. The second point is, the fact that we kind of intercept at the level of the frame buffer and not at the level of the HDMI stream. As far as our attempt to understand Linux is concerned, it makes no difference. So I think it's a permissible, apart from the fault tree aspect, it's also technically permissible, and it just simplifies the use case.
Yeah.
And maybe the third point that might be worth mentioning, when we, and Paul, it's probably you're better to chime in on this. When we created the diagram, what proved to be a little challenging before we had our brains around doing it is that the sort of the standard STPA mindset is perhaps more a human going to an ATM machine and then initiating a transaction, and the transaction initiation really flowing from the top all the way down. And what we realized here is that there are actually 3 levels. There is this top level that's an own interaction domain that generates the object model. Then there is an interaction domain that involves the rendering. And that depends on how you choose the rendering in Qt. We investigated the source code, and there are different techniques and reasons that cause the Qt library to initiate a rendering run, and the rendering really iterates through the object model with the frame rate and then produces a frame buffer. And also the frame buffer, usually there are more frame buffers involved, which we haven't shown in this diagram, of a primary and a shadow buffer that you actually, the rendering renders the frame into a shadow buffer, and then switches the frame in synchronization with the display controller, that you switch the frame at the moment when the display controller has actually reached the end of the display, that you don't kind of get this awkwardness of the display controller switching the frame buffer in the middle of the screen. And then you have so you have the frame rate driving the refresh of the frame buffer, which is somewhere between 1 and 24 hertz, 25 hertz. And then you have the display controller that uses the refresh rate for the display, which is 60 hertz, actually taking the frame buffer and turning it into an HDMI stream and sending it to the display. And it took some time to figure out that this is how we need to model it, and then how to do it in STPA, that it isn't kind of this typical top-down transaction flow.
Yeah, and I think one thing it might be worth saying is that one of the concepts in STPA is that you actually work through a number of levels of the system and kind of examine them in different diagrams to focus in on the thing that you really care about. So one of the takeaways I've got from this is that if we've identified that the actual watchdog interaction and the telltale checking part is the main thing that kind of drives our safety claim, then we could focus on that first. So we could draw a diagram which just boils it down to that part of it, but also looks at ways in which the operating system interactions with the rest of the system might interfere with that. But similarly, as you were saying, if actually our belief is that the rendering part is where most of the potential risks are, then again we can actually look at that and enumerate those and say, right, these are the kinds of risks that there are. These are the circumstances in which those risks might actually lead to losses, and use that to kind of confirm our belief that actually that's where most of the problems are, and that actually this frame buffer display controller interaction, there are fewer losses to manage there, and those are better managed. So there's 2 different ways we could kind of proceed to look at that.
What I find really nice is that we've managed to capture an STPA model that reflects the behavior pretty independent from how you actually implement it. So you could now, as you saw in the previous session, the partitioning, what do I execute on what hardware is open. You could say, I want to execute the cluster app, the rendering and the telltale checking on a simple single processor system without a graphics accelerator, in which case you then obviously from the hardware, from the actual architecture you choose, you will get different failure modes to look at than if you say it's a multiprocessor system, or it's a multiprocessor system with a dedicated rendering engine, where the cluster app and the request handler and the telltale checking definitely is executed in a part of the system that is distinctly by hardware separated from the rendering. So I think it's quite nice because the diagram just stays the same, and then the underlying hardware software architecture to which we map it changes, but all the arguments that we make at this level remain unmodified. Depending on the mapping, the only thing that happens is the mapping introduces new failure modes that come from the lower level mapping. But on the other hand, if there are already a number of failure modes you can identify here and put mitigations in place. And the nice thing is that you can then argue that some of the lower level failure modes introduced by the mapping are actually covered by the higher level safety mechanisms that we have already introduced at this system level. So they might not require additional lower level mitigation.
And
so
that's one of the.
It's really nice.
Yeah, and that's one of the really useful things about the next stage of the STPA, which is to actually go through and say, for each of these control actions here, what, in what circumstances might that lead to a hazard, and then having done that, you then actually look at there's a set of types of loss scenario which are kind of quite well described in the STPA handbook, albeit largely with a kind of a hardware system in mind. We say, look at the ways in which the controller and the controlled process interact. What could lead to this unsafe control action? So what could lead to, let's take this this read control action here from between the telltale checking and the return buffer. What could lead that to fail? And there's it might be something about maybe the telltale checking controller actually doesn't do the read because it doesn't, whatever logic is supposed to trigger that read doesn't happen for some reason. It could be that it reads it, but then the data in the return buffers is not actually hadn't been updated by the readback interface. So it's kind of based on out of date information. And then you look at each of these possibilities here, and you say what is it in my system that can manage these or detect when these unsafe conditions apply, and then having gone through that, you then have a kind of hit list of these are all the different things that can go wrong. These are the circumstances in which they might arise, and then you define a set of constraints for your individual controllers to say, what does this controller need to do in order for me to avoid these? Or if they can't actually manage that risk, then how is that risk managed by the system as a whole? So a primary example here is if the telltale checking isn't working for some reason, the watchdog will then detect this because the telltale checking either fails its challenge response or fails to do the PET. And so you have a controller constraint where a controller that's responsible for implementing a constraint on one of the other controllers, where that controller is unable to manage the risk itself.
In this part, it's also like this, that by the telltale checking and then the watchdog checking that the telltale checking actually works, although there are a lot of risks, and the most likely case to fail are in the forward path for rendering, and so like Chris, like you said, there's always the identification, the detection of this issue possible by doing the telltale checking, right? So here we at least we can go into safe state and we can make sure that we detect elements. Nevertheless, of course, it's important to have a proper forward path because that in the end, the quality and the experience which you have, but it's for safety, not the most critical path not critical path, because we could always go into safe state, but nobody would buy our product, I guess, when we say, well, we're not doing proper rendering, so we anyway go every minute into safe state or so.
Yeah, and we had a kind of conversation about that in the previous session about the potential conflict between availability and safety.
Exactly.
You need to balance them. You need them. Yeah, they both need to be honoured, but the safety claim is based on the safety part, and you just need to make sure that balances against your. Yeah, STPA kind of represents this with this idea of loss of mission being something that you can consider in your analysis as well. So you don't only, you can, in addition to considering the safety aspect, you can consider what the kind of systematic, the system level impacts are in other ways.
And this, I mean, also this is a fairly simple application. Number one, it took us quite some time that everyone was happy, that I was happy with the level of detail shown, and it was still reasonably simple that we were able to convey it. But if you look at it into it, even at this level, right, there are unbelievable challenges still around, because, for example, the rendering, if it's dynamic, then and the frame rate remains dynamic, like one of the modes in Qt supports, then it's not that easy to control the timing between the point in time when the request handler actually puts the telltale into the object model, and the rendering engine actually decides to render it into a frame buffer, and then switch the frame buffer that the display controller actually shows it on the display. Mm-hmm. So and now you can think of several ideas, right? You could say I try to derive the clock that triggers the rendering from the display controller and synchronize them. And then from there backwards, I start synchronizing the telltale checking back, and I run everything off a synchronized clock from the display controller, which clearly has implications on the kernel and on the efficiency of the kernel, because you're starting to go into hard real-time scheduling. Or you say, I leave it softer, which means that there's going to be more jitter. I accept the fact that Qt has some variation and uses some dynamic methods to decide when to kick off the rendering, maybe because the cluster application is still updating parts of the object model and hasn't committed the model yet. In which case, it's again, you can try to dynamically decipher and say, but I still use an engineering forecast as to when the telltale should be in the frame buffer. Or you go into a more decoupled mode and say, I just assume from the point in time when the telltale is requested to the point in time when it has to appear in the frame buffer, I simply set a time of 100 or 200 milliseconds. And all the telltale checking does is it waits for 200 milliseconds and says, now is the deadline is reached where the telltale has to be in the frame buffer. And if it comes later, earlier, whatever, if there is intermediate problems, I ignore it. I don't start looking until 200 milliseconds or 500 milliseconds, whatever time you want to choose after the request has occurred. And that allows for it's technically, it's a little murkier, but at the same time, it's again a simple solution, and it's okay because again the human eye is so slow.
And the advantage with taking this sort of systematic approach with STPA with this is that you can first represent all these ways in which the problems can occur, and then you can define constraints like the timing constraints that Chris was describing, or particular sort of approaches to managing those risks in the individual controllers. And because if you define those constraints in a way that you can actually then test them, you can create system tests to actually demonstrate that this is working, that you can have, you can put, apart from quite putting together the architecture, you're also putting together the design in the forms of what you're relying on the individual components to do in such a way that you can then test them, and you can demonstrate that on your actual hardware as well, so that you're sure that the behavior of the hardware is not interfering with it. And also you could do it for a specific kernel to understand whether that particular version of the kernel interferes with it. Which brings me to the other thing that which we struggled with when drawing this diagram, was that in sort of earlier versions of the diagram, we tried to represent the operating system as a box. And the main problem with that was that everything interacted with it.
Right, we had a lot of internal, we started to draw internal lines and connections. Right, yeah. I remember it, yeah.
and so instead we've focused on the functional blocks of the system, which really kind of means that we need to ask the question is, what is it we're relying on the operating system for in these circumstances? And the fact that it's not in a box doesn't mean that we can't do that, because in the end we're then looking at these individual controllers, understanding what their responsibilities are, and then from that we can say, and how does the operating system actually contribute to that responsibility? We might want to kind of examine that in another diagram, But I think in many cases, it's going to be evident when we get to the level of looking at the interactions and the loss scenarios that can kind of explain why those interactions might lead to hazards. Then the role of the operating system can become clear. So even if we haven't got it as a controller in the diagram, it can still be there.
I'm torn between two perspectives, right? The one perspective, I'd be really interested in saying, let's draw a layer that shows the operating system. And at the same time, I see that so if you look at the operating system being a coordinating instance between tasks and hardware, it would involve identifying the tasks that now are needed to run the system, plus the underlying hardware elements that are needed to interface to. And I think that model, I absolutely think it's doable. I just wonder whether it's achievable with the open source contribution effort that we have available. I think it would. I would personally, if I would have to do it, I would give myself roughly around 8 weeks to do it.
Yeah.
And if someone can do it in 8 hours or whatever, then please start doing it. I would think, because I think it takes some iterations, right? You start with the first. I mean, this is so simplified. This, for example, doesn't show any of the startup process. It doesn't show it. There are many things that are still there that we know are there, that we also see in the software. We have modeled them. And if to bring that to the system, I think you need some iterations. You start, because you don't want it to be too complex, but you don't want it to be underrepresentative of what is actually there, because then you're missing something.
Yeah. The advantage of this diagram is that it's very clear what the safety considerations are and what the actual, you were able to identify what the responsibilities of the different components of this system are. And as I say, I think the analysis will suggest ways in which the operating system is involved in that. And I think once we have that list of ways in which the operating system is involved, we're going to see examples where those are in common between the different controllers. But also if we do this for another application, we'd see some common patterns there. And I agree, Chris. I think actually, doing the analysis of those operating system components, even just for an individual application, it's still quite complex, but it's doable once you have this perspective from a particular application. And I think it would be worth doing. Whether we can do it, in the kind of the current sort of working patterns of the working group remains to be seen. But I think it would definitely be something that we could frame as a valuable exercise to do, and it'd be much easier to contemplate undertaking that when you've got an idea about how big it is or how to approach it.
A kind of a trick of the trade, right, which I think is acceptable, is to actually, from this kind of diagram, go into a strawman's implementation and then reverse engineer the intermediate layer out of the strawman's implementation, because the fact that it's sometimes easier to just write the code as an initial step to understand how the system actually works and what tasks you actually need, because you then have some first assurance. Yes, it boots, it runs, and you can then get a better understanding. Okay, how do I create a model like this? So for me, I think it's okay to sometimes one step ahead to gather some experience to then fill the intermediate step. I'm not a strict believer in that everything has to be top down, and you're not allowed to take some experience downstream and carry it back upstream and fulfill a task. And we actually spoke to the AGL guys, how complex it would be to take this into an implementation, to do exactly that step.
And I get this can also, even with starting from our reference implementation, to just go in there where do we map all the elements we already see now, right? We have the implementer. We can say that's also a bit how we came up with the object model and the rendering as 2 blocks here, and we just say, where does the things fit? And if there's something involved where we have no clue yet, or which we completely forgot about it. But I guess it's also something where we'll need to talk more to also the AGL guys and see how we bring things in.
Yeah. And I think that's that's one of the other things that we really wanted to discuss in this session is who can we get involved in this effort. I think part of the purpose of this was to prevent where we got to with it, why we think it's useful, where we think we can go with it. But I think that the big open question is who would be willing to get involved in this work? How would it be best for us to do it? And I think actually having a parallel effort to implement a demo of this, we would learn a great deal from that, and that also might kind of engage people who aren't so confident about the safety angle, but are really more confident about the implementation of some of these things and understanding the implementation. It would, then enable people with the different areas of expertise to contribute to the overall solution.
Yeah. It would be a perfect time if someone from the participants put a chat comment or also make a good proposal. Say, well, I read in the news that there's a good place to look for, to talk to other people. I guess we've even still Asian people joining, which is very late for them. So I guess for seeing this means there's interest in the topic. So maybe it's just the wrong addressing. We should look into something else. So it's something which we could ask for. I know that AGL wants to support us heavily on this. So Walt and Jan Simon did strongly in the past, and they try to do again, but I guess they're keeping it just in the internal say group of pre-contributors, and it may not be sufficient. It's really interesting to hear if there are others who would like to jump in, support a little bit in the implementation. We have the also just I guess for complete, I would share the build instructions which we have on the page GitHub.
So a good question, for example, would be you said earlier, Philip, that the previous demo was on Kimu. Would actually kind of implementing on a piece of hardware would be an interesting project. Wouldn't necessarily have to be some sort of safety critical hardware. I guess there's no reason really why we couldn't implement this something like this on or kind of a demo based on this on something like a Raspberry Pi. We'd need an external watchdog that we can interact with, but again, that's not impossible, and also that might be a project in itself as well. It'd be interesting, for example, if you could kind of collaborate with another project which would be interested in implementing the watchdog for us, and creating a demo system that we could could jointly talk about at a conference, for example.
I think as an initial kind of to understand all the additional things that you need from, in particular, involving the startup phase, then there is a ton of functionality that you don't see in this diagram here that involves ensuring that you're getting up-to-date telltale requests. So the system actually ends kind of between the vehicle and the telltale request. So you somehow need to timestamp the requests to ensure that the ones you're receiving are current and not stale, and you're continuously receiving current requests, and the outside entity that's sending the request hasn't died. So there's tons of functionality that is needed even at this level. And I think, as you said, a Raspberry Pi type implementation would be really cool. If it again, I think it requires more than kind of maybe us implementing it. It's more an enthusiastic student task, or someone who just will bring several weeks of focused time to the table to actually sit down and just implement it.
Or AGL, or somebody who's kind of interested, in bringing into being a kind of a reference platform to illustrate this. I think that would be really a really valuable thing to do.
It's also interesting to see if we make if we see the telltale request and we make the assumption that there is some kind of time stamping to see that this is also closer to reality, right? So here also from an OEM perspective to understand are there really the timestamps as we assume, or is there, I guess there is a lot of response, right? If it's can signal send, you need response. So anyway, I assume this, but these are the questions which somehow need to be written down and need to be also part of the whole concept. So not just making an assumption.
There is time stamping, and for example, there are services which you just don't see here that are managed by the kernel that maintain the time stamping mechanism, right? Yeah. So and that's where it's sometimes easier to just kind of start implementing, and then you start to see all the things that need to be added. I think at this level of abstraction, it's okay, but if we want to now take it towards understanding what does the kernel do, we would need these additional tasks, because those are all things that can, in one way or the other, potentially screw up.
Right.
So I guess, you know, from the people on the call, what kinds of work around this would you be interested in getting involved in?
Just saw the comment from beginning of the meeting from Igor Stopper, who said that wherever there's electromagnetic interference expected, there's a periodic reset of unconditionally reset, so that you get away with potential glitches and other effects which could happen. So it seemed at least he brings some experience from the industry. That could be interesting. Sure if he's still in. If you want to make call, like say there's something specific hardware which you favor or see as potential, good to take it into account. Also good feedback.
So that may be a different question, is that the other people on the call have joined this meeting to understand what, is there anything else that you'd like to understand about what we're doing in the automotive working group, or is there anything else that you think we could usefully be doing if this isn't something that you feel you can get engaged with?
Then I should maybe at least share also for those who are in the doodle poll for the automotive work group that there is a chance to join one of the other sessions which we have and to be part of saying, well, I would like to learn more, would like to get in. Just find the link again. Was sent in the automotive work group. Here we go. So we already had a few people they're named in. Currently, there's most likely a slot for Wednesday morning for Asia and Wednesday afternoon for Europe and US time. Good. Yeah, and if we don't want to change into meditation, I guess then can enjoy silence or just wait also for the wrap-up session an hour and take a little longer break than originally considered. This makes most sense. Oh.
Are there any questions from
Richard?
anyone?
Richard just dropped something.
Yeah, I mean, so I think there's some dedicated engineering time might help to frame the question, but in the end, I think the real question we have here is this something that the automotive working group should be doing? The intention of the work group is to kind of engage people from the industry. So, for example, it would be useful to actually have people from the automotive OEMs working with us. If this isn't something that they see as useful, or isn't something they feel they can contribute to, then what else could we do? Or is it that actually we should use the working group for another purpose, to gather requirements from the automotive industry rather than to actually try to work to develop a use case? I know I've certainly found it useful working on this as a way of putting the STPA methodology through its paces and see what we can understand what we can learn from it. But yes, I do see a great deal more value in then applying that to something like a kind of a reference architecture, a demo that we can then share more widely as an illustration of something, of an actual application of the approach, all the way through to influencing the design decisions and being able to demonstrate, to be able to test the constraints that we come up with. I can see a lot of value in that, but that will only work if we are actually able to engage contributors to the ELISA working groups, as well as people who are simply following the work out of interest.
Yeah, I guess, of course, with the engineering forces which we have, if we spend 1 or 2 months of engineering work, this brings us much closer to reality. In the end, we would like to reach a state where nobody can prove us to say, oh, well, it's not safe, you missed this or that, right? If we reach a point where we can say this is a system which works well from our extent, then we are in a good way. Maybe we don't achieve it as a practical way, or we have measures to do this, but that it's just that we say we have an argumentation, we can say this is how things are, we consider a lot of cases, and this brings us a good way forward. I saw you're shaking head, Chris, so maybe you have a different other view.
I think we can take it a long way. I'm not sure. I mean, taking it all the way to the point where you say you can prove that you haven't missed anything, that's just tedious, because the main approach defined in the ISO standard, simply because that's the main approach that people come up with, is introducing traceability. And once you introduce traceability, you need to introduce more stringent requirements hierarchies, and writing and producing good stringent requirement hierarchies is a lot of work, because it requires putting down a first stake in the ground and then returning and revising it as the insight in what you did increases and improves. And that also involves having someone who remains an owner for a certain set of requirements for a reasonable amount of time, because it's easiest for the guy. If I write a requirement and 2 months in the future I pass them over to you, and you have to refine them, then all the background, what was I thinking when I wrote the requirement? Was I thinking a lot? In which case maybe it's not that easy to change it, or was I just thinking nothing? I just wrote it because it was the best that came to my mind, in which case it's quite easy to change it. So the kind of the brain power of the person behind the requirement is often very important to try to change and understand the requirement. And that's where maybe the open source approach becomes a little difficult, because it really requires a more engaged ownership over a longer period of time.
Yeah.
With a team of a few people and 1 year, I think we can drive this to a really, really good level of even impressing a certification body like TÜV on showing, yes, we've achieved full traceability, it's bi-directional, and it actually makes sense. All the conclusions drawn make sense, and here's our evidence of completeness in respect to all the hardware that's involved and in respect to all the software that's involved.
Yeah.
That
it's possible, but it needs someone who's prepared to invest that amount of effort in it.
It would need a business case. I mean, for me and ARM to put that amount of time against this problem, if there is an OEM out there who says, yes, there is a concrete business case and we're interested in driving this forward, then you can put that effort against it. If it's more for educational purposes, which it's currently kind of looking at, then it's just, I'm not sure how we can overcome the heavy lifting.
Yeah, here this fits quite well to Richard's second question, where he said my second question would be, is a demo like this commercially interesting or relevant if we bring this forward? And what I just see from the automotive business from the past, I personally judge it as the telltale is a very interesting and relevant case, for the reason that if it's exactly in this model, or if it has, like we had in the previous session, if there's container technology, virtualization, other things involved, that's another question. But what we see is that 10 years back, a lot of commercial OS were there. You had a lot of royalties in the infotainment field. The infotainment field is traditionally without, it's basically QM, and there is no real demand for safety in there. But what we see is that these systems currently, fusion together. So the infotainment, the clusters, things get together. There are Linux-based things, and like 10 years back, where Linux got the way in, where replaced commercial OS in the infotainment, there's a good chance that you can also draw this for instrument clusters, because these devices with multiple screens get connected, they get centralized, and we see this vehicle computing technology, which puts a lot of ECUs together. And this brings in certain complexity, where you also say, well, okay, I have my commercial OS, but my commercial OS also need to put in a lot of efforts to get these use cases and these complex use cases where I would like to get everything in there. And I not only have the development efforts on my own, I also need to pay licenses, royalties, and so on. And then you can do the shift. And we did this. So with my previous company for Bosch and Daimler, we did this shift to the Linux-based products and sold millions of devices from it, and it was a very good invest. But it was a strong invest to first of all do this shift from a pure commercialist to a Linux-based system. And therefore you need to take the initial hurdle. Maybe we need to do an analysis. What is the eventual cost, which efforts are behind it later on? But I see that this is maybe just the logical move, and that maybe at some point of time there is the second position. If you have your market, if you have influence on this, like an OEM, to say, here is it is, bring it forward, and we invest some money so that we overcome and get cheaper offers, or maybe from a tier one side, let's say we can make a cheaper offer.
Yeah, to have a partner to work with on this, who has a kind of a commercial business case for it, would make it possible. In the absence of that, I guess, as you say, we can focus on this from a learning perspective. We can't kind of produce a kind of comprehensive set of argumentation for it, but we could focus on areas that we find particularly interesting. We can understand how to apply methodologies like STPA to it, how to then derive tests and fault injection approaches from it to kind of give us some confidence that we're actually achieving those safety requirements. I think there's a lot of things that we could explore. In the end, what we can do, how how far we can go with this is always going to depend on who we can engage in the journey.
Yeah.
Yes, what's nice about the application is it kind of does something that you can understand, and it doesn't require complex sensors and actuators, right? So an electric power steering is very difficult to and expensive and dangerous if you actually build it to utilize, because it's the sensors and the actuators are really what define the system. While here, the nice thing is you could really even on a Raspberry Pi start creating it and playing with variants, right? It would be interesting. So I think what we need to do is find a way of getting this back by something that is actually operational. That would allow us. That would bring us a huge step forward.
Yeah, I agree. You know, and even with the Raspberry Pi, if we found that actually, there were huge limitations in it, simply documenting what those limitations are, so you know what you need to address in the hardware side, would be valuable.
For the purpose of our investigation, the Raspberry Pi brings no noteworthy limitations, because, for example, supposing I'd be curious to see, supposing one splits the telltale checking, right? One introduces a virtual machine or even a container and puts the telltale checking, then how difficult does the synchronization between the forward path and the backwards path become, and how badly does it cut into the performance of the device as a whole if I put it into a virtual machine as opposed to running it as a task scheduled by the Linux operating system, right? Those questions can all be investigated with the model we have here and with the Raspberry Pi.
Yeah, and I guess if you're talking about the Raspberry Pi with external watchdog, because I think the Raspberry Pi naturally doesn't have an external watchdog, but you could simply connect it, I guess, to an Arduino, which can run as an external watchdog.
Yeah, again, in this particular case, if you a mock-up watchdog just running internally, not that you envision to be independent, just for the purpose that it serves the functionality, I think is still okay. Because even with it just the effort of porting it to these different architecture solutions and looking what impact it just takes to actually get it to run is already interesting.
Yes.
So thanks, Richard, for going a lead here and putting some question in the chat. There further question? Okay, then we don't need to wait until the end. Guess we close the session. I stop the recording. Thanks a lot, Chris, Paul, Richard, for the contributions. Hope to hear you all in the wrap-up session.